Right.
Hi, I'm Eric Spada, and that's Eric Davis. We're both architects in the NIC group at Broadcom. And today we're going to talk about hardware offload in the NIC of QUIC. All right, so I won't talk much about why we want to do transport security. I think everyone understands the pros and cons of that. What I want to really kind of focus on is why you would want to try to offload it in a NIC. So today, we're even in large deployments, there's still significant CPU cycles that are spent on encryption for transport security. There's a number of papers on this, but in the numbers quoted, anything for 10 to 30%, depending upon what assumption you want to make. The CPUs have really improved the performance of crypto operations by using dedicated instructions. And there's been a variety of look-aside accelerators in the past, but all of these have significant drawbacks from a performance perspective. You know, either memory copies in the look-aside or cache pollution in the CPU instructions. All of these things have some drawbacks. So from a NIC perspective, it's like we could do inline offload of this. And if you look at a NIC, there's a natural memory copy that happens either via an RDMA or an L2 operation for buffers that moves data in and out of the system. So if we can leverage that copy, if we can leverage that copy, we can basically get it for free from a system level. So we're not the first ones to think of this, obviously. This has been done by KTLS. It's been done by IPsec, MACsec. There's been a number of offloads like this. And finally, the other reason why you might want to do this, and this was highlighted in one of the original KTLS papers from Facebook and Meta, is you can, once the data is in the clear in the kernel, there's a lot of different telemetry and stuff you can do with XDP and other techniques to find out what's going on for pieces, depending upon your security model. Okay, so if everyone was actually checking their Facebook status or using Google Chrome, almost certainly using QUIC. QUIC is really taken off for mobile applications, and it's being used in other data center applications as well. So what is QUIC? You look at QUIC, it's a UDP transport, so it's usually implemented as a library, and it handles all the stuff that usually is done in the kernel from a TCP perspective. So it deals with packetization, congestion control, reliability, scheduling, all this stuff is done in the library, and it provides a way for them to deploy applications that have optimized transports for whatever the application is. So from a cloud perspective, this is a really nice packaging piece. It heavily leverages the industry work that we did in TLS 1.3 about cleaning up and really improving the crypto characteristics of TLS. So it uses the handshake, the crypto, all the key ladders, all are leveraged from TLS. There are two types of data transfers defined, 0RTT, which I won't talk much about, and 1RTT, which is used for most of the data transfers. The nice thing about the crypto and the way it was designed in the packetization rules is it's a much simpler protocol to deal with in hardware than TLS. So the payload doesn't walk, the header doesn't walk in the payload. There's clear packetization rules. All of the crypto stuff is self-contained, so it's really much simpler than KTLS to implement from an offload perspective. Connection IDs are used for multiplexing. They're carried in the frame, and you can effectively, multiplex different sessions, connections on top of a single socket. And there's two headers defined, a long and a short, that have different amount of information in them. So that gives you an idea what QUIC is. Now, what is a solution that we might look at for doing offload? So as I said before, KTLS and the kernel changes in KTLS did all the heavy lifting here. This was an industry effort. Our NICs support this. This was a really industry effort to figure out how to actually offload TLS into the kernel. Number of drawbacks with it, particularly in the way that the TLS is handled at the application level, but we're using that experience. So as with TLS, the setup, connection handling, handshaking, key exchange, all that stuff is done in user library. The kernel never really sees and deals with the keys. It's all handled at the application level. So one of our things that we kind of deviated a little bit is TLS uses socket options to communicate the keys and other parameters. We decided to use NetLink. It's kind of a NIC thing as well. We think it's more scalable and a better interface than socket options, but we can talk about that, and Eric will talk about that in a little bit. And then if you look at the way that the actual offload is done, you pass down the metadata about the keys in the ancillary data of the socket. And once again, we're offloading, in this case, 1 RTT short header packets. And then the kernel pretty much provides the plumbing from the UDP socket to the IP stack down into the driver. And then the driver provides the information to the NIC hardware in order to do the encryption or decryption onto the wire. So that gives you a good overview. At this point, I'll let Eric kind of go through the details.
All right, this is where we get to sum up in three or four slides, 10 minutes, over a year's worth of architecture and design. So when we talk about QUIC offload with respect to hardware, what is the hardware actually doing for you, right? So as Eric mentioned, there's two different types of QUIC packets. There are these long header QUIC packets and there's short header QUIC packets. The long header QUIC packets are the ones that are used for the handshake, the TLS handshake that occurs in the library and the application, peer-to-peer. That's where you generate your session keys, your header protection key. And then once that is done, then all the traffic, the application data is sent over short header packets. Now those long header packets, we're not offloading those into the hardware, right? The application and the QUIC library are responsible for doing all the encryption and decryption of those. But once those session keys are determined and the application data is ready to be sent, those session keys are offloaded to the hardware. So all those short packets that occur that fly through the hardware, the hardware will actually do the crypto operations on those. Now, when the hardware actually sees a long header packet, what it's going to do, it'll identify that and it'll see it, but it's not going to do anything to it. It's just going to pass it straight through to and from the wire, right up to the application, and it'll handle it. Okay. So with these short header packets, simply on the TX path, the kernel module will identify this. It'll tell the driver that this is a short header packet. One thing that we require of the QUIC library is that the hardware is not doing any NCAP or DCAP of QUIC headers and trailers. Okay, we require the QUIC library to do that. The QUIC library is managing many different connections over a single socket. It knows what flow it's going to talk on. It's very easy for it to just add those headers as it does today. So before it calls send message, it'll actually add that header and that trailer. It'll go through the stack. The hardware will see that. It'll encrypt the packet, modify that payload, and then the authentication tag will be stuck in the trailer, and then the packet will go on the wire. Similarly, on the reverse side, QUIC short header packets will be identified. Payload decrypted, authentication tag authenticated, making sure it's good, and then the decrypted packet in whole with the header and the trailer sent up the stack to the application. Okay. Now, that's one restriction. That's not restriction. That's something that we require help from the QUIC library to aid in the hardware offload. Another thing, a very killer application is if you combine UDP GSO with QUIC hardware offload, right? If you want to meet high packet rates, high performance, you're going to have to use GSO. Right? So there's even more requirements that we require from that QUIC library. Namely, in that large segment that the application is going to send down, the hardware is going to break that up into smaller packets. Okay? Each one of those small packets in that large segment needs to be wrapped and framed with that QUIC header and trailer. Okay? Just like the QUIC library was doing before on a single packet send, it's going to do the same thing with a large segment offload. Okay? Another requirement that we require in hardware is all of the short header packets in that large segment, they all have to target the same destination connection ID. Okay? If you think about this from an efficiency in the pipeline, when the hardware is actually breaking up that large segment into multiple packets, it's going to load a crypto context, and that has the keys for that connection ID. If there was mixed connection IDs while in the middle of the pipeline while the hardware was sending that, it would have to load a new crypto context for this one, and then a new one, and then the hardware would be thrashing, your performance would tank, and that's no good. So we're imposing that limit as well, that every single packet in that segment has to target the same destination connection ID. Okay? So Capabilities, right? When we look at the driver interface, what the device is going to advertise as a capability of what the implementation of that offload, what is available to the application. As this feature gets adopted, different vendors are going to implement different subtleties to how QUIC is offloaded. And the application needs to know some of these things, especially something like the cipher algorithms that are supported. Part of that handshake is I have to tell my peer, what algorithms I support, right? If I advertise something that the hardware doesn't support, I'm not going to get the benefits of crypto offload, right? So the application needs to know what algorithms are supported by the hardware. A bigger pain point is the connection ID. So the connection ID is defined by the QUIC working group. They did a really good job obfuscating these short headers. They're really hard to identify on the wire that it's a QUIC packet. And one of the ways they did that is these connection IDs are variable length. They can be 0 to 20 bytes in length. Okay, so if you think about that from a hardware point of view, and you have a packet coming in, and you're trying to match that flow to a crypto context, that's really difficult. What are you going to do? Cycle the packet 20 times looking for 20 byte connection ID, 19, and so on? That's going to kill performance as well. And to make it even worse, in that short header, the size of the connection ID is not there. Okay, so it's like this is crazy, right? So a hardware vendor is going to actually sit there and say, you know what? We're not going to support every single variable length connection ID, we're going to limit it. So we're going to support 0, 8, and 20, and that's it, all right? And the application needs to know that because the application is the thing that's creating those connection IDs and giving them to the peer, and the peer uses those when it's sending packets, okay? Additional capabilities that are more not set in stone yet, and we talk about connection migration and key rotation. These are features of QUIC. You can think about a flow that's already offloaded in the hardware. Your client could be moving. It could be moving from a Wi-Fi network to a cellular network, and it's tuple changed. It's at a different location, right? So if you already had that flow offloaded, does it make sense to have an update API into the hardware where we can just dynamically update those attributes of that flow? Same thing with key rotations as well. What we found talking to customers is those routines, those APIs aren't important because there's a lot of interaction that goes end to end between the peers for a connection migration or a key rotation that it's simpler to just do a delete of the flow from the hardware and re-add the flow with the new attributes, okay? So here's a straw man, kind of a high-level pseudocode of what the NetDev APIs would look like. So it's pretty simple. It's modeled very much like KTLS. There's going to be a flow context that's managed by the QUIC kernel module. And you can see in there you've got your connection ID, your packet number, and then based on the algorithm, you're going to have your session key, your header protection key, and your IV, right? On the NetDev, what we call the QUIC DevOps, there's going to be an add and delete, for adding flows and removing flows from the hardware. But also there's this modify command, and this goes back to the connection migration and key rotation. If the community wants to support that level of API, then there would be an update as well. Okay, so the QUIC kernel module. The QUIC kernel module is designed to be super simple. It just implements the needed plumbing between the application and the hardware, okay? And what it's doing is it's basically maintaining a large hash table of all of the flow contexts that have been offloaded to hardware, okay? At the top half of the QUIC module is a netlink interface, as Eric talked about. There's very simple commands from the application. After it does its handshake and it has those session keys, it'll do a netlink add command that'll terminate into the QUIC kernel module. And the QUIC kernel module will collate this flow context. It'll call into that NetDev API, right? It'll offload that to hardware. That'll come back successfully. And then the QUIC kernel module is going to allocate it what we call a context ID or an XID. And this XID is the key to the hash table to get to that flow context. Now, one of the reasons why we're using netlink for this versus setsockop is with netlink, we can actually return a value back to the application. So when we turn this XID back to the application, we're creating a contract and we're telling that application, every time you call send message in the future, on this flow, give me that XID back, okay? And that's sent as ancillary data to the send message call.
Yep.
So on the transmit side, what happens is the QUIC module will get this packet, and it'll look at the control message data, that ancillary data with send message, and it'll say, oh, here's the XID, right? I just do a quick hash lookup. I get that context, and then what we're doing is we're using SKB extensions where we can attach that context right to the SKB itself. So that context structure will follow that SKB all the way down to the driver. Okay, and then when the driver gets that packet, it says, oh, I have a QUIC packet. Here's the context right here. The driver does not have to do its own lookup. So there's only one lookup that occurs in the TX path all the way down, and then the driver would send that down. Similarly, on the reverse side, the hardware is actually going to, it'll do the lookup in hardware. Part of the data that comes back in the RxBD, with that decrypted packet would be that XID. The driver would do a lookup, get that flow context, and it would just pass it all the way back up to the application. So when the application calls receive message, it's going to get that XID back. So it could have a quicker lookup, right, to get to its context and its data structures versus having to parse packet headers and do all that. Okay. So finally, the SOC interface, like I said, there's this contract that we're imposing on the application. Every time you call send message, you're going to pass this XID down as ancillary data. And then the same thing on the receive side, and receive message, the application is going to get this back. So the whole entire plumbing between the application and the hardware is greatly simplified. We want to make sure there's only one lookup that occurs in either direction. Okay, and that's different from KTLS. KTLS actually does two lookups, one in the driver and one in the module. So.
Perfect.
Yep.
All right, so conclusions. Hopefully we described to you, how we would do quick offload, why it's good to do it in a device, and that the Linux changes are pretty straightforward. We're planning on uploading the driver interfaces in a pretty near future in our BNXE driver in the kernel. And then we have some separate staged QUIC kernel updates that we're going to stage first quarter next year. And just some acknowledgments. Andy Gospodarek has been the key driver from a driver and integration perspective, and he will be handling the updates into the pulls into the kernel. And we've worked with a number of customers, specifically Meta has provided a lot of feedback on this, and we appreciate that as a vendor. So feedback is welcome, big picture. Please contact us. There's been a couple of ad hoc with vendors that want to do this. Let us know, and we can put you in touch with the community that are trying to do this.
Yeah, I would add, if you know anyone that's working on a QUIC library, whether it be proprietary, open source, whatever it is, have them contact us because they can have a say in these APIs. This is all being baked right now. So
thanks.
Thank you very much. Any questions?
Did you work with the NIC software subgroup here on considering this work?
We have had discussions, but there's been some issues with us working directly with that, and I can talk to you offline about it.
Thank you.
I have one question.
Sure.
So if I QUIC application, can I just say this part is transparent?
it will.
Yeah, if your library supports it, basically you'll have no idea that the hardware will happen.
Yeah, it's the same thing if you look at KTLS today. If your TLS library supports offload, it's completely transparent to the application.
I think many of the libraries, like for KTLS, you can specify that you don't want to offload as part of a build option, but typically they'll manage all that in the application.
I've got a switch side question.
Mm-hmm.
It would be difficult to do in, say, a MACsec core on the switch, right? Because you're missing the contacts and all the key material.
For MACsec? Yeah, so MACsec is typically point-to-point. There is an end-to-end variation. End-to-end is difficult to implement in the switch, but the port-to-port, a number of our Broadcom switches support MACsec natively. And I think we actually still have some PHYs that support it as well natively, MACsec.
Thank you very much.
Thank you.
We'll go out for a short break. We'll be back at 2:40.